After all the time we've spent talking about expressions, maybe it's pretty clear by now that operators are a big deal. But there's one other thing we have to talk about, which is we've seen all these interesting operators and all of the interesting things that they do, but then there's the question of what happens if we get rid of the brackets. And this is the last thing that we have to talk about before midterm 1, and it comes down to what is the order of operations. So we already know that if we're just working with basic arithmetic, the kind of arithmetic you would work with long before you knew about C, then we have some notion of what happens first and what happens second. So here we've got an expression with no parentheses, but we know about order of operations, and we understand that even if I have no brackets in the expression, there are sort of imaginary brackets that I can use to figure out what order to do things. Those are the brackets that are dictated by the order of operations. Well, that's all well and good, and we know that for multiplication, division, addition, and subtraction. But what happens if we suddenly have tons of other operators? And first off, we can't just say order of operations. Snobs in academia wouldn't put up with that. That's too pedestrian a term. Instead, we need some fancy term for this, and so we call this precedence. And precedence refers to the generalized order of operations. Because if we're going to have a bunch of operators in our language, we need to understand what happens if there are no brackets. So if we remove all the brackets from the expression a minute ago, we end up with this. Is the result going to be the same? Is this even correct? Are we allowed to do this? And it turns out that there are some sets of operations that we can't do with or without brackets. One example would be, I'm not allowed to try something like this. Let's see, plus plus of a plus plus. That wouldn't make any sense. But that wouldn't make sense whether or not we had brackets. Here, we have a sequence of operations that, as it turns out, is valid. We don't know what it is because we don't know the values of the variables. What we want to answer today is, where do those imaginary brackets go? If I said evaluate this big expression, what would be the order of operations? Can we do this? So basically what this video is a bunch of examples and an advertisement for this PDF that I've posted, which is not my work. I've given a citation in the notes by somebody at a different university, which is this C operator precedence table. Now, there's lots of different representations of this. I found this PDF a few years ago, and I really like it. It's pretty compact, and it doesn't have any extra irrelevant information. So this is our master list of C operators. And we can see already there's definitely some stuff on this list we haven't talked about yet. So certainly whatever member selection via object name, that's going to be really exciting in November. And these two things are going to be our best friends in a couple of weeks. We won't talk about them just yet. Instead, what you'll notice is that this page groups the various operators. It turns out that they are grouped by precedence order. We call the things up here the operators with high precedence. And down at the very bottom, we'll see the operators with low precedence. And the basic rule is that if you have a set of operators in a row, the ones that go first, the earliest ones evaluated, are the ones with high precedence. And we can see here that because we have this table, we have a way of resolving that. If I have an expression involving both multiplication and addition, this table tells me that multiplication has higher precedence. That means multiplication comes first. But it also tells me how to resolve issues with, for example, if I have multiplication and a comparison operator. Well, multiplication has higher precedence, so multiplication comes first. And so I'm going to go through a few examples of this, about using the precedence table to figure it out. Now, there is one other issue, which is what happens if I have operators that are tied? And we'll talk about that at the end. All right, so let's begin by going to something more concrete. So first, just to remind us, high precedence means we evaluate it earlier. If I have an expression like, let's try 6 times 10 plus 17, or 17 plus 6 times 10, we know already that multiplication goes first in both cases. So that is to say, the imaginary brackets look like this. So what I do is I evaluate the multiplication before the addition, because addition has lower precedence. So let's start with this example. So I have removed the brackets, and I've also done another dirty trick, which is that we often write operators a certain way. So for example, we usually write the plus plus operator right up against the letter A, and I like that. And actually, to be honest, I am really appalled by this. I can't stand staring at it. But we need to know what to do, even if the operator is kept separate. We end up with weird-looking stuff like times plus plus a. We need to know what to do with this. So what we do if we have an expression with no brackets that doesn't give us any other hint, we figure out the precedence of each operator. So here, I mean, the way I would do this in a classroom is I'd put up two screens, one with the table and one with the expression. But I don't really have that option, so use your imagination. When I flip to the table, I'm going to need the plus operator, the multiplication operator, the plus plus operator, which we know is different, and the comparison equals operator, so the relational equals. Okay, so multiplication goes before addition, okay. Plus plus, this would be prefix increment, pre-increment, that's plus plus a. Postfix increment is a plus plus. So we're looking at this line here. So plus plus comes before multiplication, which comes before addition, and if we scroll down a bit, the double equals sign is all the way down here, which means we're going to do the pre-increment, then multiplication, then addition, then the double equals sign. So that means that I think the imaginary brackets look like this. Pre-increment comes first, then multiplication, and then addition, and then at the end, I do the equals equals operation. Now I've added these extra brackets on the display here because I don't want to talk yet about what we do with this, with the single equals sign. It turns out it has very low precedence. Okay, so what I've done is I've taken the expression, I've added in the imaginary brackets, and now I just evaluate it like I was doing in the videos last week. Okay, so plus plus a, I guess I should draw a little diagram because I'm using the plus plus operator. There's a, there's b, there's z, they are all int. The value of a is 6, b is 7. Okay, so plus plus a says add 1 to a, and then send back the new value of a. So this turns into 7. 6 times 7, well that's 42. And I'll just cross this out to make the display a little bit more obvious. 5 plus 42 is 47. So I've got 47 here. And then the last operation is, does this thing on the left equal b? And we can see b is equal to 7, so the answer is no. So it comes out with a 0, and z ends up with the value 0. The key here is notice that the end of that was just a review of the exercises from last week. Once I have the imaginary brackets in place, I've figured out the precedence. I just work on it like I would work on one of the previous examples. A equals 10 or 11. I'm seeing a lot of this. This is a common mistake. It's not a big deal, but a lot of people don't get what they expect out of this. And it's not actually because of precedence. When I see something like this, what this is probably an attempt to do is somebody wants to ask, is A equal to 10 or is A equal to 11? What it's actually asking is, it turns out, because not only of the rules of precedence, but because of the way logical OR works, this ends up asking, is A equal to 10 or is 11 not equal to 0? Which I can't think of a case where I really care about that. But this is a video about precedence. Let's talk about precedence. So we've got two operators, the double equals sign and logical OR. So we go look at our precedence table. Oh, we clear all the junk off of the precedence table. Okay, so there's the double equals sign, and down here is logical OR. So double equals comes first because it has higher precedence. And I'll just pre-clear this, which means that the implicit brackets go here. Okay, so is A equal to 10? And the answer to this question, well, okay, A has the value 6 here, and so this is 0. A is not equal to 10. Okay, and then I do the logical OR of 0 and 11. Okay, well, remember that logical OR gives me a value that's either 0 or 1, and it gives a value of 1 if either or both of the operands are non-zero. And of course, in this case, 11 is non-zero, so what comes out of the logical OR is 1. Now, this was discussed on a Thursday, I think, but if you do want to ask the question, is A equal to 10 or is A equal to 11, what you want is probably this. I'll just write that properly, is A equal to 10 or is A equal to 11? Remember that if you want to use logical OR, you should be tying together complete true or false expressions. You can't use logical OR as a shortcut to ask if a variable has one of a range of values. It doesn't work that way. Okay, so here's an interesting one. So it might be to some people that this doesn't need the precedence table. You could probably deduce what must be going on here, but we still should look at it. So I'm using the logical not operator, the unary not operator. It only takes one operand. And I guess then the question is, which operand is it taking? Is it saying not of A, or am I saying do this part first, A equals B, and then flip the result? So that's our question. We have to figure that out. We'll use the precedence table. The operators today are the logical not operator, exclamation point, and the double equals sign. All right, so where's the logical not operator? It is this one. You might notice that the table, one thing the table does that I'm not the most fond of is that it does use the same line for multiple operators. This is an operator called logical not, and this is an operator called bitwise not or bitwise complement. We're not going to talk about the bitwise version, so we'll just focus on this. So there's the exclamation point, and down here is the double equals sign. So logical not has higher precedence. It goes first. And that means that before I can do this, I have to already have done the logical not. And so that apparently means I should be taking not A. The not operator binds to the variable A, not to the expression A equals B. Okay, so let's just rewrite that in. Okay, so first I'll evaluate not A. Remember that what the not operator does is it returns the opposite truth value. If its operand, in this case A, evaluates to true, then the not operator returns 0. If the operand A evaluates to false, the not operator returns 1. In this case, the operand A is 6, and that evaluates to true, and so what comes out of the logical not operator is 0. Then I ask the question, is 0 equal to B? And the answer to that is no. It is not. B is 7. Okay, so here I've got this relational less than sign and the double equals sign. So we'll go take a look at our table, and we discover that the less than sign has higher precedence than double equals. So that means that we do it first. So first I ask the question, is A less than 7? Table A is 6. So the expression is 6 less than 7? The answer to that is yes or 1. And then I ask the question, is the result equal to B? And B happens to be 1, so the answer is, again, yes or 1. You might notice that if you just look at this by itself, so to be clear, final answer is 1. If you look at this by itself, this is pretty tricky, because if I rewrote this in a different order or something, it's really easy to really want to ask this question first. Is B equal to 7? But that's not what's actually happening. The rules of precedence give us one unambiguous interpretation of what to do here, where to put those imaginary brackets. All right, so here's an annoying one, and this is a pretty common place to make a mistake. So we have here a chain of logical or and a bunch of less than and greater than signs. So it turns out that we'll see later that less than and greater than are unsurprisingly pretty similar in precedence. What we care about is, okay, so where's the less than sign, where's the greater than sign, where's the logical or, where's logical and? I think that's everything. So we go take a look at our table. All right, so there's logical and is higher precedence than or. Or is at the bottom, and my relational operators, the less than and greater than sign, are up here. Notice that less than and greater than are tied. And fortunately for us, there isn't going to be a tie in our expression. All of the less than signs and greater than signs are separated by these things. So it won't be a big deal. But we need to talk later about what we do in the event of a tie. So relational less than and greater than are high precedence, and is in the middle, or is low precedence for this example. So that means that we should do the less than and greater than operations first. And then we do and, which means this and operator here happens before those two or operators. And then we do the two or operators. And in this case, we're going to just go from left to right. And I'll explain that in the next example. If I have three or operators in a row, what do I do? Well, it turns out it's left to right, but I'll clarify that point in a minute. So first question, is A less than 10? So is 6 less than 10? And the answer to that is yes, or 1. And then I've got, okay, so I first have to evaluate is b greater than 0. So b is 1. I'll just fill in the value of a. A is 6. Is b greater than 0? Yes, that's 1. Is 6 greater than 1? The answer is yes, which is 1. And I'm computing 1 and 1. And so logical AND gives me a result of 1 if both of its operands have evaluate to true. In this case, they do, so I've got 1. And then over here, b is less than 10. Well, b has the value 1. Is 1 less than 10? The answer is yes. Okay, so then I have to batch these up into their logical ORs. So there's 1. Oh, this is going to look great. Okay, I'll draw my 1s like this. 1 or 1 or 1. Okay, so I start with, I go from left to right. I start with this one. 1 or 1 evaluates to 1. And then I've got that or 1. And so the value of z at the end is 1. It's a mess. Let's just draw that out all the way. So I end up with 1 or 1, and then that comes out to 1, and then that's the eventual value of z. So in this example, it was a low-pressure case of this, but we had a tie. There was a place where we had 2 logical OR operators, and then the question was, do we go from left to right? Do we go from right to left? And we should develop that a bit. So here's an expression full of equal signs and not equal signs, the relational equals and not equals operator. And if we go to our precedence table, we will notice that relational equals and not equals are tied. They're both in the same line of the table. So neither has higher precedence than the other. So what do we do? Well, in this case, it's easy because there are brackets. We know which one to do first. What if I get rid of them? It's still a valid expression. Which a part of it do I evaluate first? And this is a concept called associativity, because we need a nice long name for it. And it turns out that our precedence table tells us what to do. If we've got multiple operators in a row, so that is multiple operators not broken up by different precedence levels. So here I've got 3 operators in a row that are all in the same row of the table. They're all in the same precedence. What order do I put in those imaginary brackets? I should be able to take any sequence of operations and install these imaginary brackets to make it obvious what I should do. So what we use if we end up with operators that are tied, that have the same precedence, is we go back to our precedence table and we look at that last column. So here we go. The last column is associativity. And it tells us if you are working with a tie in, let's say, this row, then you operate right to left. And if we go down to the row where we actually had our tie, which would be the row with the relational equals and not equals operators, the associativity column says if you have a tie here, you go left to right. And what that means is that if we have a tie, we go through our expression from left to right and just perform the operations in that order. We do this one first, the leftmost one. We then do the next one over, and then finally we do this one here. We go left to right. And if you look at the table, you'll discover that most of the operators have left to right associativity. There's only a few that don't, and one of them is a really weird one that we don't really pay much attention to in this course. All right, so A equals B equals 5. Now, this is actually one of those strange ones. This is the single equals sign. It is not asking a question, it's performing an assignment. So we don't want to go looking for equals equals, we want to go looking for the assignment operators in our table. And we also want to observe that there is a tie, so we care about the associativity. Go over here, do that, and we scroll all the way down. Assignment has really, really low precedence. You might notice there is only one operator, and it's a weird one, that has lower precedence than assignment. So all of the assignment operators, besides the plus and minus, share the same precedence. And if there's a tie, the associativity column says you go right to left. So we start on the right, and we already sort of know this. We know that assignment statements do have an inherent sort of right to leftness about them. So we go right to left. So in this case, we start over here, and we do this one first, and then we do this one. Now because there's an assignment involved, I will draw the diagram for this. We'll stop drawing my A like a 9. We come in, A has the value 6. That A looks even worse. B has the value 10, and we're about to define the value of Z. We now have our imaginary brackets, and so we just go through it. So the assignment, the right-hand side is already complete. 5, assign that to B, so B gets the value 5. The result that comes out of this would then be the new value in type of B, so it's the integer 5. We take that and we assign it to A, so A has now got the value 5, and then what comes out of these is not 6. What comes out of these is, again, the number 5, and that goes into Z. So we resolve the tie using the associativity, which happens for assignment operators to be right to left. All right, so now we've got another chain of not equals and equals. The relational equals operator. And if we remind ourselves back in our precedence table, those two operators are tied. They are both in the same row, which means we care about the associativity, which is left to right in this case. So we go over here and let's see, left to right. So first I do this, and then I do the next one, and then I'm done. Okay, so first question, is A not equal to B? Well, A is 6. Is 6 not equal to 6? No, that's false. 6 is equal to 6. This gives me the value 0. Okay, next question. Is 0 equal to 10? No. So that gives me the value 0. Is 0 not equal to 1? And the answer to this is, well, yeah, it is. It's 0, so it's not equal to 1. So the result that we get that goes into Z is the value 1. All right, so here we have another chain of those. The associativity is the same because it's the same operator, so I won't go back to the table. We go left to right. A is equal, we do that, A is equal to B, and then that equal to 10. Okay, so the first question is A equal to B? And actually, I'll clear it. Just like before, we saw earlier an example that if we glance this over and don't add those brackets, directly onto the expression, it's really easy to mess this up because there's just something about our brains that really wants to do certain parts of this first. We need to put those brackets in because there is one specific order that works. So we go left to right. Okay, there we go. First question, is A equal to B? So A is 6, B is 10. We ask the question, does 6 equal 10? No, it doesn't. Okay. Is 0 equal to 10? Answer is also, no, it isn't. So the answer to that is 0. Is 0 equal to 1? And the answer to that is, again, no, it isn't. And so we get a 0. And then there's this. You might notice we've got the word double showing up all of a sudden. So we can expect that if this is a trick question, which it is, there are going to be some typing shenanigans. So first thing, we've got the divide operator, and we need to go check its associativity. So we go back here to our table, we scroll up to find arithmetic, and there's division, and it's tied with multiplication and modulo, and it's left to right. Okay, not too many surprises there. But that means that this expression, and it's really easy to mess this up because we really want to think, we say, oh yeah, there's a double on the bottom or something. We think that means the result will be a double. Well, not so fast. First, we have to put in those imaginary brackets. Okay, so it looks like this. We go left to right. We start with A divided by 4. So what's 6 divided by 4? Well, if we were working in real numbers, 6 divided by 4 would be 1.5. But we've got an int, and we've got an int. So the result has to be an int. Okay, so 6 divided by 4 can't be 1.5. It has to just be 1. Okay, so it's 1. And then what's 1 divided by b? Now, in this case, we've got an int and a double, which means we can have a double result. So this would be 1 divided, I'll just write it in. The value of b is 10.0, so 1 divided by 10, this will be 0.1. It will not be 0.15, which is what you sort of want if you looked at the expression to begin with, because you feel like because b is a double and it's getting mixed in, that you should get that. But it isn't really getting mixed in that quickly. Because of associativity, we first do that whole a divided by 4 operation before we go any further. And there's this. I think this is the variant that's most likely to throw people off. If this were on the midterm, maybe this is on the midterm. And you may be watching this during the midterm. If this is on the midterm, I hope you get it right. If this is on the midterm, I would expect that, and people didn't see this video where I talk about this question, I would expect quite a few people fall for the trap here, which is that they really, really want to try and figure out this value first, because just the way that it's been typeset, it feels like we should work out this as the denominator. But we go and look at the precedence table, and it's not so. We notice that multiplication and division are tied, and it's left to right associativity. And that means we have a rule to follow, which is we go left to right. A divided by 4 multiplied by b. Okay, so just like before, we've got int divided by int, and the result is an int. And a is 6. And 6 divided by 4, if we assume it's an int, is 1. And then 1 times, so the value of b, which is a double, is 10. 1 times 10, what comes out of here is the double value. So I just indicate that the result of this is a double, but it's the value 10.0. And so hopefully most of these, once we got those brackets in, most of those were sort of a nice comfortable review, because once the brackets are in there, we're just doing the same thing we did last week, going through expressions with lots of different mixed operators and keeping track of types and values. But if we start from something like this, the very first thing we should do before our brains get in the way and try and make assumptions is go figure out where to put those imaginary brackets to split everything up into individual operators running one at a time. And the brackets then dictate to you what order to execute everything.